In this video, we're computing the moment of inertia for a disk, and then we're using that result to compute the moment of inertia of a solid cylinder. So to get the moment of inertia of the disk, we're doing this by slicing it into thin concentric rings, and then using the formula that we previously derived for the moment of inertia of a ring, and that's the mass of the ring times its radius squared, and I'll post a link to the video where that was derived. Immediately after finding the moment of inertia of a disk, we're going to apply that to finding the moment of inertia of a solid cylinder. So you can see in the picture, the strategy there is to slice the solid cylinder into disks, and then we use the formula for the moment of inertia of a disk that we found in the first part. So the idea for finding the moment of inertia of this disk is that we're slicing it into thin concentric rings. We're calling the mass of those dm. The radius of the rings, we call that little r. And then we want to add up the moment of inertia contribution of these rings all the way from the tiny ones close to the center of the disk to the big ones close to the outer edge of the disk. And before we get started, we need a quick reminder about the concept of area density. An area density is usually given the Greek letter sigma, so a lowercase sigma, and it's the mass per unit area. Just to make it clear what that means, the units of area density are kilograms per square meter. So it's the way you describe density when you're talking about a two-dimensional object. And the way we're going to use this is actually by turning around the definition so that we see, given an area and an area density, we can find the mass by taking area density times area. So to relate this little dm to the variable r, what I'm going to do is cut and unroll this thin ring. Then if we can find the area of that thin ring, we'll be able to express the mass in terms of our variable little r. So there's our cut and unrolled ring. And the original thin ring had a radius of r, which means a circumference of 2 pi r. So when we cut and unroll it, it has a length of 2 pi r. And the thickness of it is just an increment in that variable r. It's a dr, an infinitesimal change in r. So the area of this little ring, and I'm going to call that dA, is 2 pi r dr. And this is where our area density comes in. I can say that the mass of the ring, little dm, is given by the area density multiplied by the area of that little ring, which was 2 pi r dr. Now that we have an expression for dm in terms of our variable little r, we can write down an expression for the moment of inertia contribution of this little dm. And this is where we use our previous formula for the moment of inertia of a ring. It's just given by mass times radius squared. Well, the mass of this ring is little dm, and the radius of it is little r. So I have dm times r squared. I've already expressed dm in terms of r. That's sigma times 2 pi r dr. And we have an r squared. We can combine the little r's here. So I'll have an r cubed in the expression. And I'm going to change the order of the constants out in front because it looks better if I write it as a 2 pi sigma. And then I have an r cubed dr. Now we have an expression for the moment of inertia contribution of this little ring. And it's time to add up the contributions for all the rings. So I write that the total moment of inertia is the sum of all the moment of inertia contributions. That's what the integral means. It's the sum of all those infinitesimal contributions. So I have the integral of di, which is the integral of 2 pi sigma r cubed dr. And I'm adding up all these rings all the way from the tiny ones in the middle, where I'm close to r equals 0, to the big ones on the outer edge where I'm close to a radius of capital R. Everything is constant there except for the r cubed. So when I do the integral, I get 2 pi sigma. Then I use the power rule on the r cubed, and I get 1/4 r to the 4th. And we evaluate from 0 to capital R. Plugging in the lower limit there, I get 0 because I'm replacing r with 0. In the upper limit, I replace the little r with a big R, and I end up with a big R to the 4th. I'm going to cancel a factor of 2 while I'm at it, and I end up with a 1/2 out in front. 1/2 pi sigma big R to the 4th. And that's the total moment of inertia for this disk, but it's not a desirable way to express the answer. We want to replace that area density in terms of the mass and dimensions of the object that we're studying. So we need a little side note here that sigma is the total mass of the disk divided by its total area. Well, that's pi big R squared. So making this substitution, I find that my moment of inertia is 1/2 pi times sigma, but that's m over pi r squared, times r to the fourth. Our pi's cancel. 2 factors of r cancel. And I'm left with the famous formula 1/2 big M big R squared. Now that we know the formula for the moment of inertia of a disk, that's 1/2 mr squared, we can apply this to the solid cylinder by slicing it into disks and applying that formula 1/2 mr squared to each of these infinitesimal slices. So before we start, I want to make a point about physical intuition here. The mass distribution of the solid cylinder is exactly the same as the mass distribution of a disk. In other words, the percentage of mass at each distance from the rotation axis is going to be the same. Another way of saying this is that a solid cylinder is just a disk smeared out into a third dimension. So what I'm expecting here is that the moment of inertia for the cylinder is going to be exactly the same thing as the moment of inertia for the disk. And the point in our problem, of course, is to actually prove this by doing some calculus. So before I get started, it looks like I need to label the thickness of my disk, and I'm going to call that dx. And the length of my cylinder is a length of L, and I'm going to start my variable x from 0 on the left side to L on the right-hand side. Now, just like we needed a note about area density to do the disk, we need a note about ordinary volume density to do the cylinder. And this is normally given the Greek letter rho, and that's the mass divided by the volume with the familiar units kilograms per cubic meter. And of course, we're going to turn this around and say that if I know the volume of something and the density of it, I can take density times volume to get the mass. So our little dm, the mass of this single disc-shaped slice, is going to be the density multiplied by the volume of that disk, which I'll call dv. Well, the volume of that thin disk is just area times thickness. And the area is pi times big R squared. Every disk has that same radius of big R. And the thickness, dx. So there's an expression for dm in terms of dx. The next thing we do is find the moment of inertia contribution of this disk. And here's where we use our formula for the moment of inertia of a disk. It's 1/2 times the mass, so 1/2 times dm, times the radius of the disk, squared, and that's capital R again. So we replace dm with the expression we just found for dm. It's rho times pi times r squared dx. And we have an r squared as a spectator here. And we can clean things up a little. So we combine the r squareds into an r to the fourth, and I have 1/2 rho pi r to the fourth dx. And again, once we have an expression for di, the moment of inertia contribution of a single disk, we're ready to use integration to add up all the di's. So I is the integral of di, and we plug in the expression for di. That's 1/2 rho times pi big R to the fourth dx. And we're integrating in the variable x here as x goes from 0 to L. And that covers all the way from the leftmost slice on the cylinder to the rightmost slice. Now again, our integration variable is x. And all this other stuff is just constants. 1/2 rho pi r to the fourth. It's all constants. And we integrate dx and we get x. And we're going to evaluate this from 0 to L. When we sub in the lower limit, we get nothing. Sub in the upper limit, and we get a factor of L. And as usual, we don't want to express the final answer in terms of the density of the object. We want to get it in terms of the mass and the dimensions of the object. So rho is the mass of this object divided by its volume. That's big M divided by the volume of the cylinder. And the volume of a cylinder, again, is the area of the base. So pi times big R squared times the length or the height, depending on the orientation. And that's capital L. So we're going to replace rho with M over pi R squared L. Making this substitution, we get 1/2 times rho, which we now replace with M over pi R squared L times pi R to the fourth times L. And the pi's cancel. 2 factors of R cancel, leaving me with an R squared in the numerator. And the L's cancel. And I'm left with a moment of inertia for the solid cylinder of 1/2 mr squared, which again is what we expected because it has the same mass distribution as a disk. It's just a disk smeared out into a third dimension. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.